The challenges of quantum computing in the near future. The advent of quantum computers is likely to revolutionize the way we approach data protection. Unlike classical computers, quantum computers harness quantum mechanical effects, such as superposition and entanglement, to process and store data in a form beyond the zeros and ones that are digital bits. These quantum bits or qubits could offer massive computing power, but they also pose significant challenges to data protection. Quantum-safe cryptography. To address these challenges, a new field of cryptography has emerged: post-quantum cryptography. This approach involves developing cryptographic algorithms that can evade hacking by quantum computers, using programs that can run on a regular laptop. Several groups of scientists are racing to develop these algorithms, which could provide a vital layer of protection against powerful quantum computers. The foundations of cryptography dates back thousands of years, with the earliest known example being a cipher carved into ancient Egyptian stone in 1900 BC. The cryptography used by most software systems today relies on public key algorithms, which involve factoring the product of two large prime numbers to generate both a public key and a private key. Challenges for classical computers to crack such cryptography. Hackers and other malefactors often must factor the products of very large prime numbers or try to find the private key by brute force. This is a hard problem for classical computers because they have to test each guess one after another, which limits how quickly the factors can be identified. Massive computing power. A 100-story skyscraper on a 3-story building illustrates the challenge of cracking quantum-safe cryptography. Currently, classical computers often stitch together multiple encryption algorithms, implemented at different locations, such as a hard disk or the Internet. However, most of this cryptographic infrastructure was built on a foundation developed in the 1990s and early 2000s, when the Internet was much less central to our lives and quantum computers were mainly thought experiments. The need for post-quantum cryptography. It's like a foundation for a 3-story building, and then we built a 100-story skyscraper on it. It's like a foundation for a 3-story building, and then we built a 100-story skyscraper on it, Michel Mosca, co-founder and CEO of cybersecurity company EvolutionQ, said. Structural lattices and hash functions. Several groups of scientists are racing to develop cryptographic algorithms that can evade hacking by quantum computers. Some of these algorithms rely on newly developed equations, while others are turning to centuries-old ones. The National Institute of Standards and Technology, NIST, is currently looking at 4 problems as potential foundations for post-quantum cryptography, 3 of which belong to a mathematical family known as structured lattices. These problems ask questions about the vectors between interconnected nodes, like the connection points in a spiderweb. Calculating the shortest vector in the lattice, trying to determine which vectors are closest to one another, creating a key using the vectors between nodes. Hash functions work by taking the virtual key for unlocking a specific point on a data table, scrambling that key, and compressing it into a shorter code. This type of algorithm is already a cornerstone of modern cybersecurity. The 4th problem that NIST is considering belongs to a group called hash functions. Other potential algorithms. The European Commission is looking at an error-correcting code known as the Michaelis cryptosystem. Developed more than 40 years ago by American engineer Robert Michaelis, this system uses random number generation to create a public and private key, as well as an encryption algorithm. The recipient of the private key uses a fixed cipher to decrypt the data. Michaelis cryptosystem advantages. Description security. Michaelis encryption is considered both faster and more secure than the most commonly used public key cryptosystem, Rivest-Shamir-Adleman. Key size. The keys to unscramble the data must be processed using extremely large, cumbersome matrices, requiring a lot of energy to run. No silver bullet in the race to find quantum-safe cryptographic equations. There won't be a silver bullet or a one-size-fits-all solution. For example, there's always a trade-off in processing power. It wouldn't make much sense to use complex, power-hungry algorithms to secure low-priority data when a simpler system might be perfectly adequate. Trade-off in processing power. Use of complex algorithms to secure high-priority data. Use of simpler algorithms to secure low-priority data. Cryptographic agility. In fact, It's valuable for organizations that use classical computers to have more than one algorithm that can protect their data from quantum threats. That way, if one is proven to be vulnerable, you can easily switch to one that was not proven vulnerable, Rebecca Crothamer, a technological ethicist and CEO of cybersecurity firm QSecure, said. The importance of post-quantum cryptography: the sooner we can protect sensitive data from quantum computers, the better. There's also the chance that, again, because quantum computers are so powerful, we won't actually know when an organization gets access to such a powerful machine, Crothamer said. The future of post-quantum cryptography: in the future, post-quantum cryptography will not be an endpoint. The arms race between hackers and security professionals will continue to evolve well into the future, in ways that we can only begin to predict. It may mean developing encryption algorithms that run on a quantum computer as opposed to a classical one, or finding ways to thwart quantum artificial intelligence. The world needs to keep working on this, because if these post-quantum equations are broken, we don't want to wait 20 years to come up with a replacement, Michelle Mosca said.